Hi, welcome to this tutorial on pyelmer. I'm going to show you the example heating up water, which is a very simple test case that consists out of a domain with two squares. One is the bottom square with water. The square at the top is filled with air. It's all in steady state. We have a heating at the bottom with a temperature of 80 degrees Celsius, at the top 20 degrees Celsius. There won't be any heat flux over the boundary, and I will consider only heat conduction, which is actually not that physical but makes the case easier to understand. Here you can see the code for the example that I copied from the pyelmer GitHub page. I will go through this in some detail now. It first starts with some import. You could just copy this if you don't understand it. Then I set up my working directory and start with the Gmesh modeling. This is just some initialization that is required by the Gmesh API. I'm using here the Open Cascade kernel that I give the name factory to not have to use this clumsy expression always. I create two bodies that are just rectangles with the water at the bottom with the origin 0, 0, 0 and the side length of 1, and on top of it is the air body. I have to fragment these two bodies in a bit clumsy way here. That is necessary when you use the Gmesh API. Then I create physical groups. For this I wrote my own function that is just a bit simpler and saves you some lines. You give it the dimension of your bodies. This is the rectangle that we just created, and the name water, and the same for the air body. To detect the boundaries, I also use my own function, which is this get boundaries in box. By hovering your mouse on top of this, you can see a description of it that comes from the code in pyelmer. The arguments are the minimum and maximum coordinates, and the dimension and the tag of the parent entity. In this case, it's the bottom boundary that I want to detect here. It belongs to the water rectangle. With this detected boundary, I create in the physical group and do the same for the air boundary at the top, and create a physical group again. I set the mesh size, generate a mesh, and with this command I can visualize my setup. I now run this file. Then you see here in Gmesh the domain with the two bodies, and with Ctrl-Shift-V you can select the different physical groups. Water at the bottom, air on top of it, the bottom boundary is here, the top boundary there. So looks like we have set up everything in a nice way. Here I have the Elmer set up. Always start in pyelmer by creating a simulation. You could either say your simulation is a simulation object that you just create, and then you give it some settings in a dictionary style where you can write anything that shall be in the settings section in your zip file, but you can also directly load this simulation. In this case, to the steady simulation, and this load function goes into the pyelmer database and looks there for a simulation named 2D steady. In the documentation you see you can also give it your own setup file. I don't use this here, but if you have your own setup file, you can just provide the path to this YAML setup file. It has to look the same way as the file on the pyelmer website does. I just show it here. It's in the pyelmer data and simulations, where some examples are available. Here This is the one that I'm using with a Cartesian two-dimensional coordinate system, steady state, maximum 10 iterations. Okay, then I load the same way again my materials into my simulation. It's also predefined in a YAML file for air and water. The solver is also already there. I'm using this heat solver, the results output solver, and creating an equation. You could, if your solver is not there, again say solver heat equals to elmer.solver. You need to give it the simulation in name, call it heat solver, and some data. This data is a dictionary, and yeah, there every solver parameters belong into. So again, returning to my database for the solvers, heat solver, that's the one that I'm using. All this is into the data dictionary. But as I said, easiest way is to directly load the solver from the database. With the solver, we create an equation just consisting out of this heat solver. If you have several solvers, just add this in the list. We have an initial condition with a fixed temperature. Here I'm using the dictionary style expression. The boundaries are, no, that's not the boundaries, that's the bodies. A body for water. Create a body object belonging to my simulation with the name water. And this is a link to the physical group water that we created with Gmesh. It has a material that is water. This is the one that we defined up here in the initial condition, defined there, and an equation here, the heat equation. Same we do for air. Then we only have to define the boundary conditions, and then we are ready to go. For this we use the boundary class that we again have in the Elmer module. We add it to our simulation with the name bottom. The physical group bottom is the one that we defined here with Gmesh on top. And we want to set a fixed temperature. You also have different options available depending on your case. For example, we could also set a fixed heat flux, but this is not our case here, so I'll delete this. The same we do for the top boundary. Here I just modified the code a bit to show you a different approach, which is similar to the way here. So here I'm using this predefined parameter fixed temperature that I assign a value to, but instead you can always use the data dictionary in this object, and here I would update it with the Alma style boundary condition that shall be written into the zip file. In this case this is useless, but if your boundary condition is not available in pyelmer, you can add any other boundary condition in this dictionary style way. Then yeah, I write the start info and the zip file into my directory, and I'm ready to do the simulation. I just take here the execute module that I imported on top, one Elmer grid in my directory, giving it the mesh file name that I exported from Gmesh. Here it still says that you need to use the legacy, but it's not valid anymore, so you can use also the standard Gmesh output. Then I run the solver in my directory. It's always looking for a case.sif file. And once the one is completed, we scan our log files and print the output. Then we execute our script again and see in our sim data it creates the mesh file and the solver one creates a log. There's also a log for the Elmer grid. Everything looks fine, as we also see our function here prints the errors, warning statistics. There are no errors and warnings. The statistic, it took 0.13 seconds to run this case. Then we can open this with ParaView. Have to hit apply, select the temperature, and we see it's everything the way we expected.